I don't know if you all, we probably have talked to Portunus already one time. It's the system simulator. So now what we can think is what's the difference between a system simulation and a component design, and where really is the boundary between system simulation and component design. Sometimes there is not so much of a boundary. It kind of actually goes together. So you can see here we actually have a device, or we have the device by itself right there. This is the generator itself. The generator eventually is actually integrated in a grid, and then we have a machine which has a controller. So if I look at the device itself, the machine itself, this is the component. But once I take this whole thing here, now I'm actually having a full system. So there are devices, there are components inside there, but I'm looking at them how to work together. So the important part of a system simulation is you have a lot of modeling flexibility. If you do the component, you're bound by the geometry, you're bound by the physics and everything. Here you're going to be able to take some shortcut. You're going to be able to simplify some of the computation. You're actually removed from the model itself, so you don't look at the details of the device, but you look at the way it behaves. So maybe for a machine, you're not going to look at the distribution of the flux, but you're going to look at the inductances. And that's what you're going to try to take inside the system. And then the software itself adapt itself to a particular application. What I mean is that with an electrical circuit scheme, we can do thermal computation. That's what AutoCAD does. It takes a topology and it changes into a thermal circuit. That's the idea, actually. Okay? So that's another type of ID. Component level, we have the semiconductor, we have all the different styles that are here. And on the system level, we actually look at the network signal flow, and then we look at event. So semiconductor turn on, turn off. A switch just blow off or something like this. This is what actually we do. So if I take the car as a full system, in it I have different components. And all of those actually goes and build the whole system. So let's, what do we need to actually do a good system? So those are the different things, and I'm going to go through all of those different things. Library, modeling flexibility, graphic interface, efficient simulation solver and stuff like this, programming interface and software. This one is important because you need to be able to extend. So it's very important to have a possibility to program other science inside the system. And this one are also important because we're talking systems, so this means we're going to have many components and we want to be able to link them. So that's the few important things. So efficient technology here, what do we have? Simulator technology. So it's Portunus actually works on a combination of analog and digital solvers, both of them at the same time. And you can see them here. Those are PetriNet or state graph or things like this. So what are those? Those are state-driven events, condition-driven events, state. So I'm in a certain state until I reach a condition, then I'm going to the next state. So for example, I'm asleep, I wake up in the morning, I'm awake. I get hungry, I eat, and I'm not hungry anymore. It's time to go to work, I go into my car, etc. Those are all different states and different things that I can add together. Of course, I take them this way, but it's also to control semiconductor. So, for example, between the current is on until I reach a maximum value of the current. Then it's off. Until somewhere in another component the current goes down, then my current is on. So you can imagine you can drive anything you want like this by those different conditions. So that's the digital part. And then the analog part, which is right there, that has, I mean, this, you know, all of this. This is just an electrical circuit. So you have your machine, rectifier bridge, DC link, and then you have all the inverter, and then another type of machine. So a generator, for example, and a motor on the other side. And then eventually some block to actually one other stuff. The other thing important is we need to be able to do transient. We need to be able to do operating point, DC, and AC. So all of this Portunus knows how to do. Solving highly nonlinear system. Of course, if we do all of those things, everything is nonlinear. So it needs to be very stable. That's important. Switch system. We want to be able to adapt the step size. Why? Because if I go, for example, if I follow this sinusoidal, just looking at it, I can have I need to have a fairly small, I can have a time step that increases until I go to the top here, and now I need to decrease the time step to get the run on the top, and then I can increase again. Same idea here. As long as I'm in the state, I can increase the time step. However, when I reach the condition, I need to cut the time step. So I have the point before the condition and after the condition. So that's the adaptable time step control. And then multi-simulation support, be able to do multi-simulation at the same time. Something we've done actually, because we said the solver needs to be very stable, we used to work only with Euler and Trapez type of approximation, and we actually use a new method, and this method actually brings up a little more stability. I'm not going to work much on this because I'm more interested about the interface. So other things, we need the good GUI. So first thing is we have a drag and drop library. So here we have a library. You can see you have a voltage source, you have a current source, and other things like this. So I can actually text this voltage source, drop it somewhere. Well, like any other tool. Nothing special here, okay? Other thing is that this is the drop. So I can have the component-specific dialog. So I'm looking at this machine, and I can open, and now I say I have a three-phase voltage source. I have all the characteristics associated to the source. I have the RMS value or the peak voltage, frequency, phase, and eventually an offset in voltage if it's necessary. So for each component, I will have their own dialog box. We have online display. So that's actually the same type of display you can find in Flux. You can actually get values. You can get min, max. You can get a point and anything like this. You can adjust the stuff. Symbol animation. This is kind of cool because I'm going to be able to follow as I go along. So, for example, those three state graph drives those three branches. So one is the on/off on the top, off of the bottom, and the other one is the reverse one. And then the condition to actually do the PWM. So as I'm solving, I will be able to see those diodes lining up. They will show me when the current goes through. Same way, there is a little arrow. We don't see it here, but it's right there. This arrow will show me the current flowing through. So all of this is animated. I can follow as I go along. Same thing here. The state will see the point going from state to state. That's another cool stuff. So that's the symbol animation, and then we need to be able to do parameter variation. And the parameter variation I have right here. So I can actually select a parameter. So this one is, not really sure which one was this. It's one of those parameters. And then I give a variation, I can solve for this variation. So I can get full type of computation here. We can have multiple page, do some system, library management, user interaction, replay mode. Replay mode is important. When it's solved, I can actually go look at it again, and I can even slow it down to see what's happening. So that's the multiple sheet. So where we get here, we have, you see all those little pins, they go to another one. So here, I have others, the input and the output. And then after I get another sheet. So I have a sheet for the thermal part, a sheet for the computation of the power dissipation, and a sheet for the display. So you can, it makes it very easy to manage actually. Curve post-processing. Not much. So automatic resize of the graphic in X and Y as it's solving. If you use MATLAB, you know that it's not the case. You have to ask for resizing to do it all the time. Undo, redo option. You can change the curve, the thickness, the marker size. You can select whatever you want. You can export the curve, even in a screenshot. You can have two cursors, so then you can get the value between the two cursors. You can have a different type of views. You can do zoom on zoom, multi-Y, so you can have several curves on the same Y. I mean, all the stuff you actually get on all of the type of computation we do. Other things it has today, which is I think very good, is the project manager. So the idea is, once you have a project, you can exchange it with other people. So you can do versioning. You add something, you can keep track of all those versions. You can send the whole project to somebody else. They will be able to see where you are. Parameter variation, we said this is very important. So I'm going to be able to do the solving for variation of parameters. Subsheet and libraries. So a subsheet, for example, here I define a subsheet which is a rectifier. I have 3 inputs, 3 outputs. I can describe the symbol. Then I can describe the inside, so it's like a macro, okay? And then I can put all the information associated to the macro. So again, that's allow you to make general components and use them and bring them and exchange them also, by the way. Okay, I just told you all of this. Real-time and user interaction. So, for example, here it's a box where we have a PID controller, and we can change on the fly the different values of the different coefficients of the controller. And so you can see, as you go along, you can see here we have a certain setting that the users kind of move maybe the KP, and now you have a bigger oscillation. And as you go along, as it's solving, you can interact. You can switch on and switch off. You can do a lot of those things as it's going along. Variable definition. So this is a full variable definition. You give the name of the variable, you can give a table for the variable, you can enter the value. That's all inside there. And then you can get the curve of the variable itself. So here we just did a step, and we say is that if the time is, so the variable is named variable n. So it says it's basically a double precision. If the time is less than 10 milliseconds, then the variable is, okay, the time is bigger than 10 milliseconds, the variable is 10, otherwise it's 1. Here you get the function. So you can get any function you want. And yes, and then the editor, you can see it's colored. It's colored, so you can see that you don't make any mistake. It helps you do avoid the mistake. The different animated symbols, we have little needles, we have a digital counter, we have the on-off, we saw the diode, the state machine, and then if you do a short circuit, it will indicate where you do the short circuit. Another interesting, important part. And this is where we get to the next part. When we get actually a connection to something else, we'll be able to bring in the symbol of the something else. So at a given time, I can bring, for example, a color-shaded plot from Flux and look at it right there as it's going along. And then, so for example, this is a solenoid that is moving. We have the core position, and then at given position, I can say, give me the value. And you can even export information to a web HTML dialog, and you can even go to do web simulation. But I'm not going to say much about this. This is an extension of what we do. It does also animation through other tools, other party tools. This is actually, that's a nice sheet. We showed this one quite a bit. Again, it's a Prius car. So you have the drive of the machine. You have, here is the thermal engine, the internal combustion engine, ICE. We have the planetary gear. We have two machines. One is the generators, the other one is the motor itself, and then the whole problem. So with a third-party tool, we can actually see the car going up and doing stuff like this. System description. Well, we have all the dialogue we need for the system description. We have the network, electrical network, the state machine, we talked about it, the block diagrams, and then we have VHDL AMS, which is keyed in, so you can actually code anything you want, and then you can bring cables. So this is the, if I'm not mistaken, those are the IC tables, time-dependent characteristics. And okay, also the C++ library. VHDL-AMS, maybe you know what it is. It's a standalone language that is actually kind of controlled, normalized by the IEEE. Portunus has been identified as one of the two most compliant tools on the market. The other one is Simulink or whatever. It's a company in Sweden. So know that we have real VHDL-AMS language inside there. Okay. If I look from this side, it's better. Here we go. So, for example, here are two different ways of modeling. So, what we're modeling here. This is an exchange into, what do we have here? It's defining a signal, okay? We have a voltage here, and okay, this is an exchange between tables, I think, of a table of flux and voltage. So that's the whole block that you'd have to do if you were doing the block diagram. So you can see quite a few blocks and connections. VHDL-AMS, you just do this in 4 lines. Okay, so one of the advantages of using this kind of things. Another example here, we have a stepper model, and this is the equivalent circuit network approach. This is a VHDL-AMS. So equivalent circuit approach, what I'm going to have to do is define the logic of those switches here, depending on the position. In the VHDL-AMS, I have the voltage source, I have the 2 bridges, and I have the 2 phases of the machine, and basically the rotor, and just those 4 boxes. So, of course, I need to put the code in. Yeah, that's true, but it's a little more efficient too. And here it shows you the result with the VHDL-AMS. You can bring in SPICE model also. It's compliant 2G, no, it's higher, maybe 4G8 or something like this. Model library. So we have the regular network, electrical network, the block diagrams, the state machines, SPICE, VHDL, C, C++. And we have this for power tuning. We have the thermal, we have a magnetic library, a mechanic library, and an electric library. And all of this added by scripting capabilities and stuff like this. Lookup table. So now that's another story, because in the table you give digital value. So you give different value at different time and stuff like this. And so what you have now is you have an interpolation. You don't have, here is the just step interpolation. There used to be a linear interpolation. So if I do a linear interpolation and I derive the curves of the derivative is going to be those steps, which can give trouble when you solve a transient, okay? Now if I do a spin interpolation, then the derivative is going to be this continuous and derivable quantity. So we have an interpolation that goes inside the table, and we do have it also for the 3D tables. Same idea. So quite an advantage also right there. The FFT post-processing, same idea. There is no limitation in the number of harmonics. Before we were limited to 50, which means that now I can actually get a full signal and go to the, assuming I have the samples to do it, of course. If you don't have the sampling, you cannot do it, okay? This is an FFT of the trapezoid functions, and you can see it's not straight, but it goes, there is a rise time. And here, that's the, this is the FFT that you get, and basically the theory and Portunus are right on top of each other. Programming interface, we said this is important. So there is a C++ interface completely inside the library. So we have a DLL which is created automatically, and we created DLL in the C interface. We can bring it into the library and use it in the schematic. So here we have different type of interaction, Excel, MATLAB, etc. We have a Portunus that we can get out, and we can go out around. We can control this also. Software link, and that's where I want to get. So we have the possibility to connect with speed. So which means from speed we can bring the decomposition of the machine and bring it right there. And now we have a first level type of machine, and we can solve it. So here are some different type of results. MotorCAD, same idea. We can bring the thermal network for MotorCAD inside Portunus. Why would you like to do this? Well, sometimes if you want to compute the electrical side and the thermal side at the same time, for example, that's a way to do it. Also, if you want to make the circuit more complicated because you have other type of elements, you can also do it. There is a whole thermal library, for example. And then connection with Flux. That's where I want to get. So different type of co-simulation, and I'm going to show them in a few minutes here. And I think probably, okay, connection also to Inca. So what it's going to do is that it's basically exporting a net list of Inca. So for example, we have the net list of this full bus bar and power module together. So we can actually compute it in Inca, get it out in Portunus, and do a system simulation with it. And then furthermore, because all of this needs some time to control, and Portunus doesn't have the pretension of doing control, so you can actually connect to Simulink to do the control. And then this is the other software that you do animation. That's essentially post-processing. Here it shows you the different things that you can do.